Good afternoon, everybody, and welcome to the very last presentation of this symposium. So my name is Miriam Schuster, and today I'm going to talk about AM glass with a special focus on thinner glass with a higher stiffness. And all the work that I'm going to present today is a joint work with some project partners and the Glass Competence Center. And for the Glass Competence Center, I also want to mention Matthias Seel and Amir Shadeh. Amir is also here today, and he is writing his PhD thesis about the AM glass. So today I'm going to start with the motivation and the potential of AM glass in the built environment. Then I want to give you an example of thinner glass with a higher stiffness. I'm going to present shortly some AM glass technology and the challenges that we have. Then I'm going to talk about some tests that we already conducted on AM glass components, and I will close the presentation with a summary and outlook. So as we have already seen in this exhibition and also in this symposium, some materials are already more frequently used for AM in the built environment. And here we have, for example, steel, concrete, or polymers. And printing glass is neither very new. However, as we see in this picture, it is more used on a smaller scale, like in the optics or in the electronics. When we are looking at the glass in the built environment, then we have a much larger scale. So we use it, for example, as a facade element. And up to date, we can now produce glass sheets with dimension of 3 meters 20 by 20 meters, which is very, very large. So we see that, we are in different dimensions than the AM glass currently is. So, and the aim of our research is to combine all of those three circles, so the additive manufacturing of glass for the built environment. So when we are looking again at the built environment and the glass, we see that the biggest potential is that it is a transparent material, and that's why it is very often used. We primarily use soda lime silicate glass, and it is used as a facade element, as we see in those pictures, but also as a load-bearing structure, as we can, for example, see in the second picture, where we have a stair in an Apple store, and we see that the staircases are made of laminated glass. We have a fall protection, which is also made of glass, and we can even see some beams made out of glass. One trend is to get bigger glass panes to have individual and customized facades. This is, for example, shown in the first picture. This is the Crystal House in Amsterdam, where some glass bricks were used for this facade. And on the right-hand side from this slide, we see two other very customized facades. In the third picture, we see facade elements with an X. Here, molds were used to create this X, and this X had two advantages. The first one is it is a cool design, and the second one, it brings some structural advantages. Because of this X, we have a higher bending stiffness, and because of that, we could reduce the glass thickness. And in this case, it was also possible to use then some point fixings instead of some linear load-bearing conditions. On the right picture, we see another very individual facade. The top of this glass pane is structured, and in fact, we had here at the beginning a glass pane with a thickness of 10 millimeters, and then the structure was created with many facet cuts where the glass was removed up to a thickness of 6 millimeters. So in order to get such individual facades, we have to make a huge effort, and we need a lot of energy or have to remove some material. When we are now talking about the potential, I first want to show an example of a staircase. Here we see again the stairs and the connection to the walls of the stairs, which in fact are some linear bearings. And now we could imagine that this connection of the stair to the wall could be made by AM. So that's one possible application. Another one is to talk about or think about point fixings. So traditional point fixings in the facade are either glued to our glass elements, or we need some holes in at least one of the glass panes, and then we are connecting our point fixing in that hole. And the disadvantages of those conventional point fixes is that we need a glue, so we have adhesives, and or we are weakening our glass structure with a hole. And we could avoid this by using some AM glass connections. And the first idea of such a connection was already shown at the Glass Tech, where we created a flipped desk. And in this flipped desk, we had at the four corners some AM components. So there were some glass volcanoes printed. And then we placed them on a glass sheet and laminated it together to a laminated glass. And then, just installed it as a flipped desk. Another potential is to reduce the thickness of glass and to stiffen it with some reinforcements. And here I see two applications. The first one is shaping thin sheets, as we could do it in a similar way as shown in this picture. In this picture, we see thin metal sheets. These are pictures from a former colleague of us who was doing his PhD about the van of thin metal sheets. And we could do this or adapt this procedure for thin glass and create very individual designs. Another possible application would be to have simply flat glass as we usually have it in our facade, as for example here, and print some ribs on it in order to increase the bending stiffness. So we want to have the behavior like on this picture, but we want to avoid removing material. Instead, we want to print some extra material on it. So that's the idea. And here we have two advantages. Of course, we can save some resources since we need less material for the same bending stiffness. And we can modify our design of the glass sheet. Here we have one very specific example. So this is a glass plate with the dimensions of 1.50 meter by 1 meter. And we have a linear support at the shorter sides. So the span is 1.50 meter. And in order to fulfill the serviceability limit state according to the German standard, we would require a glass thickness of 9.1 millimeter, which actually is not a standardized thickness for glass, so we would even go for the 10 millimeter thick glass. However, by modifying these glass sheets by only 3 reinforcements with dimensions of 40 millimeter by 10 millimeter, we could reduce the thickness of the glass plate to 6 millimeters, which is huge, since this means that we have a material saving of approximately 30%, which also means that our structure is lighter, which is very advantageous for the transport and also for the installation. Now I want to present some AM technologies. I don't want to go in more detail for the powder and resin processes, since those are limited to smaller scales and we need really large scales in the built environment, which is why I want to show some people or institutions that are dealing with extrusion processes. So here on the left-hand side we have the MIT, and the MIT was the pioneer in printing glass. And on the right-hand side, we have Maple glass printer, which is actually one of the companies that is able to print larger objects. Here we have other persons and institutions. So, for example, we have here Micron 3D printer, extrusion print on a plate. We have Ilmenau and the Laserzentrum Hannover. And on the right-hand side, we have the Notre Dame, and the special thing about this last picture is that they are using hollow tubes, which are then printed. Here we have another picture. This is by Nobula. And with this picture, I want to show that for all the extrusion-based technologies, we have in common that we are printing layer by layer. And when we are doing this, then, of course, we have the interface between the layers, and there are some notches, and those notches can be a weak point, especially for brittle materials as glasses. So what are the challenges? The challenges can be divided into different levels. So the first level would be the printing process itself. Glass has a very high melting temperature of more than 1000 degrees Celsius. So we are dealing with very, very high temperatures, and we need to control this temperature and the viscosity of the glass during the process. And as we already heard during other presentations, there are even more parameters that can be played with, and we need to find the optimal combination of all those parameters to get then a result that we really can use in the built environment. So the second level of challenges is to characterize the result of the AM component. And of course, we want to remain it transparent. And this means that we don't want bubbles, we don't want to have some crystals, and so on. However, we also need a very good mechanical performance. And therefore, we want to avoid that our AM connection is the weakest point. And instead, we want a very homogeneous connection. Another problem is that due to these high temperatures, we have some temperature gradients in our base plate and also in the AM components, and therefore we have some thermal residual stresses. And we need to control them too in order to be able to design with it. There are some further challenges. As I already said, glass is a brittle material. So when we aim to use it, for example, as an overhead glazing or fall protection glazing, we need to fulfill some safety aspects, which means that we probably need to adapt our post-processing processes, which means that the AM modified glass sheet needs to be laminated to another glass, or we need to try to increase the stress by thermal tempering processes. Another problem that was also already talked about today is the upscaling. So until now, we are working on a kind of small scale, but in the built environment, we need very large scales. And of course, then we have, again, the problem with the residual stresses. Here I want to show some examinations that can be done at different levels of the AM process. In the first picture, we see a thermographic picture. So we use a thermographic camera in order to monitor the temperature during the printing process. And when we finish the printing process, then we can use photoelastic measurements in order to check the residual stresses in our printing component. So that's here the second picture. Then we can use CT scans in order to create some 3D models and to check whether there are some density differences in our component or if there are some holes or other imperfections. We can also do some mechanical testing. For example, we can determine the hardness of our sample. So these are the three lower pictures beginning from the left, where we did some indentation tests on a printed wall, which was on a base plate. And here in this graph, we see the hardness on the y-axis, and on the x-axis, we see the position on our printed object, and the black line is the interface of the base plate and the printed wall. And we can see that there is almost no difference here in hardness, which is good, which means that we have almost constant material behavior. We also performed some load-bearing capacity tests. In this case, we have here a shear test. and I want to present this a bit more in detail. So here we had samples. Again, we had a base plate, and on this base plate, a wall was printed, and this printed wall had dimensions of approximately 25 by 6 millimeters and 6 millimeters in height. And this wall was printed with a laser glass deposition process, and this was done by the Laserzentrum Hannover. Then we took those samples and installed them in our testing machine. So the printed wall was linearly supported, and the base plate was pushed downwards. And the test was completed when failure occurred. And here we see the maximum loads during those tests. So we in total tested 10 samples, and see that the mean value of this maximum load was about 2.9 kilonewton. And comparing this to a possible application, which would be the staircase, which is held by the consoles on the wall, we see that this AM console needs to be a load from 1.6 kilonewtons, which is lower than the maximum load that we achieved in our tests, which is good. So then we are also able to produce some digital twins of the actually printed samples. Those digital twins can then be used for finite element analysis in order to determine the maximum stresses, for example. And after breakage, we also looked at the fracture mirror in order to check where was the fracture origin. And here, this is very interesting in my opinion. So we expected 3 different failure modes. The first one would be that the crack migrates through the glass plate. The second one, the crack migrates in a crescent shape. And the third mode would be that the crack migrates through the AM glass wall. And actually, in our test, case 3 did not occur yet. So I think we had in those 10 tests that we did, we had a very good connection between the AM wall and the base plate. So I want to summarize. We see different applications of AM glass in the built environment, starting from point fixings or linear bearings, but I think the biggest potential lies in the stiffening of thin glass. I showed the example that, where we could reduce the glass thickness from 9 millimeter to 6 millimeter by only applying 3 reinforcements. And we did some shear tests where none of the samples has broken at the interface of the base plate and the AM wall. Now coming to the outlook, at the Glass Competence Center we are currently building a glass 3D printer who is using the FDM method. And in this printer, we see it here in this picture, we are able to print on a base plate with the measures of 200 times 300 millimeters. This is the first version of a 3D printer. We are already planning the second version, where the aim is to print on a base plate with a size of 500 times 1000 millimeters. However, this is still small, so our vision is to go for very, very large printers, or to be able to print on the largest glass panes that are currently available with 3 meter 20 times 20 meter. Then there's another thing I want to present to you very briefly. I have talked about that the biggest advantage of AM in the glass field could be to print some reinforcements. And instead of printing reinforcements, we are also looking at local deformations of glass and stiffening it in that way. And here I have a sample where the glass was locally deformed, and here we have then a linear reinforcement. And this is even less material, so maybe also a very, very good option in order to reduce the glass stiffness. So that was all from my side. I tried to be quick. I hope it was okay. If you have some question, don't hesitate to ask. If you want to join our AM glass network, just contact us. Thank you.
Thank you. Are there questions for the last speaker of the day in the audience? Well, then I start. In the MIT printing glass was shown all over, especially in the architectural design world, especially because of the light effects we see. I was wondering if you're looking at methods to design. We also see it in the points plates that has a quite high impact on the localized texture of glass. So I was wondering if there was designing the reinforcement, placement, or geometry combined with the potential light or texture effects that might have on glass.
That's a very nice one. It's a really good idea. We did not think about that yet, but we should, yes. Thank you.
Maybe we can think about it together.
Yeah.
Yes.
Well, you have no more. Ah, great. Thanks.
Thank you for the presentation. One question from my side. What's about durability? So what will happen during the time if you use glass as cantilever? Because of its amorph, and will it degrade during the time?
No, not really. So glass has a really good durability. The problem is more when we have glass in combination with polymers, for example, that then we have a creep behavior during time. But I'm not sure if I really get your question, but...
Yes, maybe so it's more about creep during the time.
Yeah, no, normally it's not the problem since the glass transition temperature of glass is very high. It's above 500 degrees Celsius, so we don't have the viscoelastic behavior in the normal temperature range.
Thank you.